Hi, Dr. Churchill for Astronomy 305. Welcome back for Module 3, the Universal Context of Life. And we are going today step out and take a true viewing the wider world look-see. We are going to look at the universe as a whole. We're going to do some real astronomy today. I'm going to bring you to the cutting edge of human knowledge in talking about our cosmos. And I hope you got some appreciation from our previous lectures about how one does science, that it's a process of forming a hypothesis, from seeing observations of seeing things, and then from a hypothesis making predictions, running tests, which are experiments to see whether your predictions hold true or not. And through that, we learn how to refine our ideas. So we have refinement of ideas. Once in a while, we have a whole new theory that comes along, which changes our view entirely, what we call a paradigm change. We gave some examples of that with Einstein and with Copernicus. And what I want to say is that that process really was born or developed to fruition only about 400 years ago with Galileo, and then beyond with Isaac Newton. And in that time, we have gone from thinking that we lived in a little solar system with around a star to that there are other stars out there, maybe they have planets around them, to realizing that we're in a system of stars that is one of another 100 or 2 or 300 billion star systems we call galaxies, and from beyond that, the larger universe. And it's only in the last 30 years that we have come to understand the structure of the universe. And I'm going to share with you something today, a knowledge of something called the cosmic web. Well, 30 years ago, we didn't know this existed. So I'm trying to let you know that even in my own lifetime, we've had complete changes and growth in our understanding of what's going on and what the universe is like that we live in. So today is going to be the Astronomy Day, and we are going to talk about the true context of which life has developed in this universe. Now you might be wondering what this whack job picture I have behind me is, and that, ladies and gentlemen, is a picture of the history of our universe on one page. Now, it may look kind of funny and wacky to you, but how do you portray the cosmos in one picture? It used to be that some cosmologies thought that the universe was, a turtle floating on water, and the turtle had elephants on its back that held up the sky. We have a different cosmology. We have one in which there apparently was some energy burst that we call the Big Bang, from which then it opened up a chism, if you will, of space and time, which has been which is pliable and has been growing and expanding and passing ever since. So I'm not going to get into what all the things are in this picture, but it's just for fun. Just, there's this bright spot on the right that's representing the Big Bang, and then you have a rapid expansion from that point, and you see then that as the universe is expanded, that some structure has developed, and it looks like long filaments of things with beads on a string, and that is our modern view of the large-scale structure of the universe. And then this period, a little bit more toward the left before you bump into my head, where you start to see galaxies forming and stars forming. And then coming all the way over here, you can see that the universe has become much more open, and the space between the galaxies has seemingly emptied out, and the galaxies themselves form these ecosystems of stars and gas, and we live in one of these galaxies. So today I'm going to talk about this a little bit. I'm not going to go into the total history of the cosmology, which would be its own lecture and would be fascinating. But I am going to talk to you about how old the universe is and how big it is and how we fit into it in terms of planets and stars and galaxies. So I'm going to share my screen and we're going to move forward with this lecture today. Okay, so hopefully you guys can see this. We have chapter 3, the universal context of life. And what we're showing here is a gas cloud that is what we might say is a stellar nursery. And this is just one little blip inside of a galaxy where stars would be forming. We'll talk more about that in a bit. Okay, some learning objectives. We're going to talk about life in the universe. And so what are the major lessons that we learn about the context of life from studying the cosmology itself? And then we want to know something about the structure and age of the universe, 3.2, and what modern science has taught us about that. I can't tell you the whole history, the whole story of how we've learned each of these things, which to me would be a fascinating thing to lecture on. So we want to then know the next two bullets about, what is the age of the universe, how long has it been around, and then how big is the universe. Okay, so then we might want to talk a little bit about the nature of worlds. How do you form stars? How do you form planetary systems? How do you form worlds? And what different worlds are there? Okay, so we have our solar system, which we'll talk about the structure of. It has a variety of different planets in it, but what we want to know is if the variety of planets we have in our own solar system is similar to or unique or different than others. And so we'll talk a little bit about the work that's been done on that just in the last 20, 15 years. And then we'll talk a little bit about whether planets that are habitable are common. And we'll really talk about that in modules 11 and toward, I think it's 10 and 11 toward the end of the course. We're going to come full circle back to that, okay? What I do want to talk about are a little bit also are the chemical elements, 3.4, the universe of matter and energy. Mostly I'm going to be talking about the chemical elements in the periodic table and how that fits together. We talked a little bit about what light was, what is light and what is energy under bullet 3.4. That light was electric and magnetic energy. And I think we learned a little bit that, being trapped on the Earth, all we can do is collect light energy from the far reaches of the universe. And then we have to apply the laws of physics to the object that emitted the light, and therefore from that physics learn the nature of the object that emitted the light. And that is how we have discovered everything we know about the universe. And so in red writing down here at the bottom, I've kind of given you a quick shot in the arm walk away of our universe. And if you remember the movie with Carl Sagan's optimistic statement about the universe should be teeming with life, some of these things I'm about to say are the reasons why. Okay, so you live in a cosmic ecosystem. Your planet orbits a star, which is one of 100 billion stars in the galaxy that we inhabit, okay? Which this galaxy is one of 100 or a few hundred billion galaxies in the universe, okay? So how are the stars distributed in the galaxy? How are galaxies distributed in the universe? We've only known that for the last 30 years. Each galaxy cycles gas into stars and planets. These are formed and then they go through a life process where they age and evolve, and then they basically die. Stars die in the sense that they blow up or they give back their gas to galaxy, from which then new generations of stars will be built from that gas. And so it's a true cycle, okay? The cycles that this happens on are on the order of billions of years to several tens of billions of years. The universe itself is 13.6 billion years old, okay? That's a time enough for a few generations of solar systems to have come and gone in our galaxy alone, which is about a 10 billion year old galaxy, and our sun is about 5 billion years old. So there's been multiple generations of solar systems that have existed in our region of our galaxy alone, okay? Whoops. Let's see. The universe is so huge that the numbers of possible sites of life as we know it to persist is an astronomical number, on the order of the number of stars in the universe, which is this 1 followed by 22 zeros, or in scientific words, 10 to the 22. And then you can whittle it away from there as to like, well, how many of those stars have planets around them, and how many of those planets are habitable, and how many of those planets did life form on. And you start chopping off zeros here so that you maybe get down to 100 million or something like that, possible planets where life could form in the universe. We'll talk about that also toward the end of the class. We'll do an exercise like that. It's called the Drake equation. But this is just to tell you that this is the number that we're sort of starting with as possible number of stars in the entire observable universe, okay? Now, one of the things we're also going to learn is the distance between these places makes them virtually unreachable as far as we understand physics. Now, that's using today's technology, and it's very possible that we might learn something about physics that will allow us to have faster than light technology, a warp drive, if you will, hyperdrives, if you will, depending on whether you like Star Trek or Star Wars. And I firmly believe this is going to happen because we're learning all kinds of amazing things, such as, maybe you've heard of it, it's called quantum entanglement, for example. And this is something that's been understood very little, that allows information to travel limitless distance in basically instantaneously. The trick is that the two things that are communicate have to be entangled as a quantum system, which is very unstable and very difficult to do on a macroscopic level. But people have successfully carried out experiments to do this. You should look it up if you're interested. It's called quantum entanglement. Excuse me. I know, bless you, quantum entanglement. It sounds like I need to have somebody say Gesundheit. Okay, so let's move on with our important ideas, if you will, okay? So, okay, if you're gonna study the universe at large, you are definitely going to have to build on some pillars or axioms of knowledge that you have to believe in order to make any headway. Okay, so let's frame the context. We have 3 bulleted points here. The universe is vast and old, the elements of life are widespread, and the laws of physics are universal, okay? So that last one is going to turn out to be a very important assumption. Okay, so right now, the universe is very old. Its vastness implies an enormous number of worlds in which life could have possibly arisen. And its old age means that there's been plenty of time for life to evolve and take hold. And even for something like us with intelligence, intelligent life, though 2020 has really challenged my thoughts on that about humanity. Okay, the elements of life are widespread. We're going to talk today about how life is made up of very few chemical elements, basically about 5, and that these are the most abundant elements created in the universe, in this cosmos, And that is really quite interesting. So the raw ingredients for life are ubiquitous. Okay, so we'll talk about that. And last but not least, a very important idea is that the physical laws, as we have determined them or measured them, the theories that we have to operate universally throughout all space and all time in the universe. So way back 13 billion years ago, atomic physics was the same. And 400 million light years away from us, atomic physics is the same. So that is very important, because if we don't think that light and matter interact physically the same way in the past, then how in the heck can we interpret what information is in the light and figure out what the matter was like in the past? Okay, also the same thing holds for where it was in distance or location. And we will talk about how time and location are tied together in a minute. Okay. So it's reasonable to think then that life is possible, and that the conditions for life, if you want to say, are possible in all of these different locations throughout the universe, if the universe around us as we see it and observe it is the same everywhere. Now, I can tell you that this has to be true to a high level of precision, or we would not be able to make any sense out of the light that we collect, and therefore probably not put together that picture back there. The other thing I want to say, and this was an experiment that I was actually involved with, there is a way to measure some of the physical constants of nature through light that has passed through the universe for the last 10 plus billion years. And so we've done this experiment to measure something called the fine structure constant, not only just what it is today and here on the Earth, but what was it at different directions in the universe and at different times in the universe. And we've been able to do that. And it turns out that to the precision of all of our measurements, which is about 1 part in 100,000 or 1 part in a few 100,000, that these constants have not changed. And it's very important because, if these constants changed, atoms as we know may not even be able to exist. And in fact, that does bring us to the idea of fine tuning in the universe, which is to say that maybe nobody's told you this before or not, I don't know, but if you take all the atomic constants, you take all the constants of nature, like the mass of the electron and the mass of a proton, and like the constant for the strength of the electromagnetic force. If any of these numbers, of which there's about some 20 odd numbers like this, if any of these change by a few percent, as much as 5, 10%, the whole universe just goes poof. That we know it. I mean, obviously it would be some different universe, but it would not be a universe that we could live in. Our bodies would not function, biology would not exist as we know it, chemistry would not exist. Maybe even atoms wouldn't bond, or the periodic table of atoms may not exist. And so this is also a quandary that we have to try and understand with time. Okay. All right, so let's move on now. So this slide is the one in which don't worry, the pretty pictures are coming. This slide is the one where I want to tie together the concept of distance and large distances, and then eventually tie that in with something called look back time. Okay, look back time. All right. So we're going to be addressing these questions. Where and when do we fit in? What are the main structures and how are they related relative to each other? What are the relative sizes and how are they located? And what is the cosmic ecosystem for the process of life? That's what we're going to end on today. All right, so let's define some distances. I'm going to be using terms like light years and maybe even something called parsecs or megaparsecs. Okay, everything's always mega and giga and big. Okay, but let's talk about first a unit that works really well on the scale of the solar system. This is called the astronomical unit. Okay, that's this one right here, astronomical unit, or AU. So you'll see something like 1 AU. That means 1 astronomical unit of distance. That distance is the radius, or I should say that distance is the distance from the sun to the earth, okay, or the radius of the earth's orbit, which of course isn't a perfect circle, but it's only 3% out of round, so it's pretty close to a circle. The average distance of the earth from the sun, okay, the average radius of the earth's orbit, and that turns out to be about 93 million miles. Okay, it's a long, long, long distance. Or if you want light kilometers, it's about 150 million kilometers. Okay, now that gets you around the solar system pretty well because you know the Mercury is like 0.4 or 40% of an AU, and Venus is 0.7, Earth is 1, you know, Mars is 1.5, Jupiter is 5. Saturn is 10, and Uranus is 20, and Neptune is 40, okay? And so off we go. It gets you around the solar system really well. But when you start talking about the distances between stars, then you have to use a much longer distance measurement. And we use a distance measurement that's called the light year, okay? Now, look, I know that sounds weird. Distance is a light year? Yes. It's a distance that light travels in a year, okay? So you can see down here at the bottom that we've talked about the speed of light and how fast it is. 180,000 miles in 1 second, okay? Ladies and gentlemen, that is 7 times circling the globe of the Earth, unless you're a flat earther, okay? That's 7 times around the Earth in 1 second. That's fast, okay? So 180,000 miles per second. In kilometers, that turns out to be 300,000 kilometers per second, okay? Excuse me. So then you might say, okay, so it can travel, you know, 180,000 miles in 1 second. How far does it travel in a year? Okay, well, it turns out if you take the fact that there's 60 seconds in a minute, and there's 60 minutes in an hour, and there's 24 hours in a day, and there's 365 days a year, and you multiply all that stuff together, you get there's about 31,500,000, give or take, seconds in a year. 31.5 million seconds in a year. So take your 180,000 miles per second, multiply it by your 31.5 million seconds, and you get a very large number. And it turns out that if you do this in terms of kilometers, I'm sorry, if you do it in terms of miles per second, you get about 600 trillion miles in a year that it travels. And if you do it in kilometers per second, you get about 10 trillion kilometers in a second. Now, I can't even fathom those distances, but that's how far light will travel in a year. And that's our new yardstick. That distance that light travels in a year is our yardstick. And it's about 10 trillion kilometers or 6 trillion miles, okay? All right, so the astronomical unit and then the light year, both measures of distance. But what we're going to see here is that the light year is tied to time. Okay. So what I want to do now is talk about the sizes and relative structure of some things in a very quick overview, and also discuss that in terms of light time, if you will. I should, you know, distance measured in light years, but also something called look back time that we're going to talk about, okay? Okay, so Here's box number 1, planet Earth. Here we are. Okay, it's about 10 to the 4 kilometers, about 10,000 kilometers on a side. Okay, light can go around it about 7 times in 1 second. So 7 times around the Earth is about 186,000 miles or 300,000 kilometers. Now, the Earth is in a system of planets. I know people know this. The sun is at the center, okay? And then we have Mercury, we have Venus, we have Earth's orbit, the 3rd planet out, then we have Mars. Then coming out about 5 times further is Jupiter, and then double that, you got Saturn, and double that, you've got Uranus, and then outside there at the very edge is Neptune. Now, these are not to scale, but it gives you an idea. And so here's our little planet inside of this box. This whole stretch here is somewhere around 60 astronomical units, okay? So let's now talk about the size of the solar system in light distances. I know, like light years, but we're going to use light minutes and light hours. Okay, for example, how far does light travel in a second? 300,000 kilometers in a second. So we would say that a light second of distance is 300,000 kilometers. All right. Well, when light leaves the surface of the sun, traveling at 300,000 kilometers per second, it has to travel this 150 million kilometers to get out to the Earth. How long does that take? Okay, you get out your little calculator and you come up with 8 minutes and 20 seconds. Okay, so light takes, when it leaves the surface of the sun, 8 minutes and 20 seconds to travel out to the orbit of the Earth. So when you look at the sun, not recommended, if you look at the sun, you're seeing light that left the surface of the sun 8 minutes and 20 seconds ago. So you're not seeing the sun as it is right now because the information you collected is already 8 minutes and 20 seconds old. You are seeing the sun as the information of the sun, and so you are seeing the sun as it was 8 minutes and 20 seconds ago. This, ladies and gentlemen, is called look back time. Okay, it's the amount of time that you're looking back in history. Okay, it's very fascinating. When you actually observe the sun, you're seeing it as it was 8 minutes ago. So in 8 minutes from now, okay, think about the light that's now striking the Earth in 8 minutes from now, and you will know that it had left the sun while I'm talking right now. Okay. All right, so we can talk about distances in terms of light time, travel time, okay? 8 minutes and 20 seconds to reach the Earth, okay? Jupiter is about 5 times further, so that's about 40 minutes for light to travel out to Jupiter, okay? Well, it takes a long time to get out to Pluto. It takes about maybe 6 hours to get light out to Pluto. So we could say that the Earth is eight light minutes away from the sun. We could say Jupiter's 40 light minutes from the sun. Those are distances now. And we could say that Pluto is something like 6 light hours from the sun. Okay, or I can't remember if it's 6 or 12, but several hours like this. And so we might think, well, how big is the solar system from one side of Pluto's orbit to the other? And you're saying, Pluto's not a planet. Well, I'm just using Pluto as the extreme object in my example, okay? And it would take about half a day for light to travel from the sun to Pluto. Therefore, from one side of Pluto's orbit to the other, it takes twice as long. It takes about a day. So you could say to somebody, the solar system is about a light day in diameter. And what does that mean? It's the size of the solar system is the distance that light travels in a day. It's one light day across, okay? Now, let's move on. We're going to take our solar system and put it context to our galaxy. So here we're going to shrink our little box down to some little pinpoint that you can't even see here. in this object of a system of stars. Excuse me. This system of stars is about 100,000 light years across. Okay, now I'm using that light years thing because we're out there now. It would take a light beam to travel it would take 100,000 years for it to travel all the way across our galaxy. So look back time, let's talk about that. If you were on a star here and you were observing light from a star that traveled all the way across here, you're now collecting the light. It left there 100,000 years ago. So you are actually observing this, you're observing the star as it was 100,000 years ago. So the look back time is equal to the light travel time. You know, if it took 100,000 light years to cross, then you're seeing it as it was 100,000 years ago. Okay, let's talk about some numbers here, which we will repeat a little later in the lecture, but we are about, this is a spiral galaxy, as we call it, has about 100 billion or so stars in it. The average distance between stars is on the order of about 10 light years. The nearest star to us is about 4¼ light years away. It is a rotating system in the sense that the planets rotate around the sun. The sun itself is a star here with its little rotating planets around it, and the sun itself is being carried around the galaxy in its orbit around the galaxy. All the stars orbit around the center of the galaxy, and the galaxy takes about 250 million years to rotate once, which is to say the sun takes 250 million years to orbit around the galaxy. The sun's about 5 billion years old, so the sun has made about 20 orbits around our galaxy. Okay, this galaxy, which is typical, is a member of a group of galaxies. So in the sense that planets are grouped around stars, and stars are grouped into galaxies, galaxies are grouped into groups as well. And we're going to find out even sometimes very large groups. We are a member of a group of about, say, 50 to 100 galaxies, and we don't know all of them yet because some of them are very small and dim, but we keep finding new ones every year. But effectively, we have one large sister galaxy, which you may have heard of, called the Andromeda Galaxy. So here's our Milky Way galaxy. Our sun is embedded in there, about 2/3 the way out from the center, orbiting around once every 250 million years. And there's this other galaxy that's about 2 million light years away. And it's rotating around too, and it has some couple 100 billion stars in it as well. And these galaxies are moving relative to each other. It turns out that they're kind of moving toward each other a little bit, and it's expected that about 3.5 billion years from now that they're actually going to collide. There's so much astronomy we could talk about that we can't, but colliding galaxies, the whole topic. Okay, now this group of galaxies then is in a larger context, and this is called the local supercluster of galaxies. So not only is the galaxy in a group, but the group then is one group of many in a supercluster. So you could think of a galaxy as, like, you know, a house, and that this house lives in a city, and that the city is in the suburbs of, say, a metropolitan area like New York City. Okay, I know it's silly, but it's helpful to think about that way. We live in the suburbs of a very large cluster of galaxies, which is called the Virgo Cluster. And this cluster has hundreds of thousands, well, thousands to tens of thousands, and then in this whole volume, it can be up to hundreds of thousands of these galaxies in these groups that are called large clusters. Okay, it is odd that we actually live out in the very far outskirts of these clusters, and galaxies that are living clusters are experiencing harassment from one another because they, over their lifetimes, do kind of collide into each other now and again. But we're out here where it's pretty quiet. you know, true farmland, if you will. Not a whole lot going on out here in the suburbs of the local supercluster. Now, we'll show later, this background is not just haphazard. It sort of shows these little filaments and these bubble shapes that are three-dimensional. This is called the cosmic web. And it turns out that these clusters form at the intersections of these cosmic webs. So let's look at this little area right here. You can see a filament coming together, a filament coming this way and one coming that way. And in the intersection of those are these superclusters. And so our supercluster might be like right here, for example. Of course, they're showing it there. But if it was here, and then we would be in one of these little outskirt filaments here between these clusters. Okay, and I'm going to show you that in more detail coming up. Now, again, let's think about the light that came from the Andromeda Galaxy and we happen to observe it. That light takes 2.2 million years to reach our solar system in the Milky Way galaxy over here. So when we collect that light, it's 2.2 million years old. And now we're collecting it and we're figuring out that information that is basically what the galaxy was like 2.2 million years ago. So that is the look back time to the Andromeda Galaxy. Some galaxies are 400 million years, 400 million light years away. Some are as far away as 10 billion light years. So we're seeing those galaxies way back in the early history of the universe, okay? So I want you to understand that, you know, I've come home from the telescope with light that I've collected that's 10 billion years old. It has information on it. It tells me how the universe was 10 billion years ago, okay? And so, again, that's why we call it look back time. And if you know how far an object is in light years, if you say, oh, that's 10 light years away, that means that you're seeing it as it was 10 years ago. The information you're collecting is 10 years old on that object. I know I've said it 1,000 times, but I just want to make sure you get that concept. All right, so now let me talk to you a little bit about our local area of the universe. We're going to start by looking at our local filaments coming in to our cosmic web, and then we're going to blow out and show where we are in the larger scale of the universe. Okay. So we talked about the fact that we live in a local group. So you might think of us as being one of the galaxies in this little circle here. This circle would have a diameter about 1 million light years across. Okay, so it takes light 1 million years to cross that little circle. That's our little local group. And you can see we're along on one of these filaments here. Okay. Milky Way is about 100,000 light years across. So it's literally about maybe 10% the size of this circle here. All right. Now, you take this circle and you blow out on this image here further. And this is the local group circle here that we have. And this is our Virgo cluster. This is our big, you know, tens of thousands of galaxies cluster that are, they're all gravitationally bound to one another. The distance that we live from the center of this Virgo cluster is about 65 million light years, okay? Excuse me. So, as you know, that means it takes light 65 million years to get there. So when we look at the galaxies that live in the Virgo cluster, we're seeing them as they were 65 million years ago. Okay, so let's put that into context. Let's say that this blob in the center is our Virgo cluster, and we're out here in one of these filaments, our little local group. The Virgo cluster is at the intersection of some very large filaments that are coming together in this overall structure we call the cosmic web. Now, what are you looking at? This is actually not a picture. This is not some kind of photograph. This is actually an image from a computer model simulation, okay? And each one of these bright points in a sense, is a galaxy or a cluster of galaxies or a group of galaxies. When they get so many of them together, they get blurred together. But you can see the individual points are galaxies in this cube or volume of the universe. Okay, this bar here is about 100 million light years across. Remember, we were about 65 million light years out, so we're about out here, okay, from this cluster. And this bar is 100 million light years, which is about 1% of the size of the observable universe, okay? Okay, so you can see that this is a very complex structure showing the filaments. These things are gravitationally clumped together through their gravitational attraction to one another. And again, I want to say that we did not understand this overall shape, these filaments and these filaments coming together into clusters and where we were relative to the clusters. We didn't understand that as early as 1990, okay? So in 1990, we didn't know that. And then two things happened. Computers got really powerful. And when people modeled the universe to try and understand it as it evolved, and I will show you a link to a simulation later, the computer model started showing this structure. And we thought, wow. At the same time, we built a telescope called the Sloan Digital Sky Survey Telescope. It's up at Apache Point. It's 2.5 meters across, and it scans the sky, and it measures the distances to all these galaxies and their location, whether it's off to the north or off to the south. So we know its position on the sky, and we know its distance, and we were able to make maps of the galaxies. And by the year 2000, we were able to confirm that the computer simulations were getting it right, that the universe is formed into this web-like structure, and galaxies reside on these filaments, and the filaments fall into areas where there's more dense matter and form these big clusters of galaxies. Okay, so this is the structure of the universe as we know it today, and it's something we've only known 30 years. Okay, now if you take our little square from before, okay, and you put it in the context of the broader universe, you see that this structure keeps going, okay? It is a huge cosmic web, every bright point a galaxy, all along these filaments, okay? This bar here is 1.5 billion light years across, okay? Which is about 10% of the size of the universe, the observable universe. The observable universe is some maybe 90 to 100 billion light years across. Okay. Don't ask me to explain the difference between what the universe is and what the observable universe is. Okay. But the observable universe is about 100 billion light years across. Okay. So you can see now that the computer simulations do a bang-up job of measuring this large-scale structure, and that we've been able to compare it to the data in very sophisticated ways. It's not like, oh, gee whiz, it kind of looks the same. I mean, you go into the computer models and you measure things called three-point correlation functions that tell you the relative distances of all the objects to all the other objects. And you get out this shape of that, and then you measure it for real galaxies, and you compare them. And if they match, they're consistent with one another, then that's telling you that the computer models are doing a pretty good job. If the computer models aren't doing, the measurements of the models aren't matching the data, then we go into the models and we turn some knobs, and we try to figure out what are we getting wrong about the physics, and then run the models again, and then compare them to the data and see if they work. And that's how we get the computer models to really look a lot, not just look or appear, but actually quantitatively match the observable universe. Now, I thought it's always fun just to show this slide. On the left is a brain cell with its neurons and dendrites. And on the right is our Virgo cluster with the filaments of the cosmic web. And it's kind of very interesting that we have sort of what we call a fractal, unfolding in the universe, that the human mind is structured in order to be very good at transmitting thoughts and developing memory and in connecting dots, symbolism, all the things that go into the human mind, that the universe is structured pretty much the same way that the human mind is. And so I think that's really kind of an interesting thing that I'd like to share with everybody. Okay, so there's a quote here by David Bohm. David Bohm was a physicist who was very famous, who was really trying to understand consciousness in terms of physics. And he has this quote here that, in some sense, man is a microcosm of the universe, and therefore what man is a clue to the universe, and we are enfolded in the universe. Okay, a beautiful picture of natural science is that humans, or life itself, are a natural outcome of the expression of the physics of the universe. And if you watch Jill Tarter's TED Talk at the beginning of the course, I hope you realized that she said, evolution of humanity is not an end all. Words and phrases like the ascent of man are completely wrong, and they need to be completely wiped out, because the development of life is a random process that is just biology and chemistry working toward to survive and preserve its reproducibility. Sounds dry, but it's a miracle that's beautiful, and it's also a miracle that is a natural expression, and therefore, why wouldn't it reflect the natural physics and morphology of the universe? Okay, now let's talk a little bit about the age of the universe. Okay, 13.6 billion years is the age of the universe. 13.7, give or take. Okay. In the 1990s, we didn't know whether the universe was, say, 6 or 7 billion years old or 25 billion years old. We really knew it was old, but we didn't know exactly how old. We had some ideas that it probably had to be older than 10 billion years. And there was a crisis that there were some objects in the universe that we measured their ages, and they turned out to be older than some models of the universe were of the universe's age. So how can you have objects in the universe that are older than the universe itself? And so that was a crisis. But we developed some space satellites, one called Planck after Max Planck, and one of them called COBE, and one of them called WMAP for the Wilkinson Mapping Telescope. And these three telescopes helped us really constrain the age of the universe in ways that I can't go into now. But the precision of the measurements for our cosmology are on the order of around 1%. So we know, for example, how old the universe is to within 1%. And so it's 13.6, 13.7 billion years old, okay? And we know something about the expansion rate of the universe, whereas before we didn't know that very well. Now we know that extremely well within a few percent. Gosh, there's so many things I'd like to talk about, but there is a crisis in cosmology right now where two different measurements are getting different answers for the expansion rate. They're pretty close together, but the precision of each of the measurements are so high that we can't reconcile the two measurements. And one of them has to do with local measurements of the universe and then figuring out its expansion rate. The other one has to do with measurements that go all the way back to the light that is emitted from the Big Bang, and it gives a slightly different answer. And this really is one of those flies in the pudding that we love, because how can you have two different expansion rates? One was measured using local information, one using information that's 13.6 billion years old. So which one's right? Maybe there's some physics we haven't figured out, okay? So that's exciting. But I can't tell you about all those things, and I can't get into the details, but I just want to let you know that we're constantly battling these things, okay? It's spectacular. Okay, so the way that we can talk about 13.6 billion years of time is to collapse it down into a model that we can visualize. And the model that we can visualize, you can see from the slide, is to collapse all 13.6 billion years of time down to the length of a year. And then we can talk about the equivalent sort of length of time that passed in the universe on the calendar year. Okay. Now, if you do this, if you say, let's talk about the collapse the history of the universe down into one calendar year, it turns out that one day out of the calendar will correspond to 40 million years having transpired in the universe. And 1 month would transpire to about 1.1 billion years transpiring in the universe. So each month is a little bit more than 1 billion years having transpired in the universe, okay? Where the Big Bang would have happened at midnight of January 1, and today would comprise basically midnight of December 31st at the end of that year. Okay, so let's go through the calendar a little bit here, and we have the Big Bang on January 1st, and then not a lot's happening here. We get the formation of hydrogen and helium, which I'll talk about a little bit later, and then we have these sort of dark ages where no stars exist yet. Gas hasn't coalesced down into stars, and then some stars can start to form a little bit. So I keep going to May. The calendar goes this way. So these dark ages here, and then some stars start to form and galaxies start to form. And we see that somewhere here in early February, a couple billion years, about 1.5 to 2 billion years in, we see galaxies like the Milky Way starting to form, okay? And time goes by, and time goes by, and stars are being born, and stars are dying, and solar systems are coming, and solar systems are going. And then it's not until September 3rd, with all of that ecosystem in our galaxy going on, and all the other galaxies, similar ecosystems doing similar processes, it's all the way till about early September, September 3rd, that the sun and the earth form. Okay, the sun and the earth form. So a lot has taken place in times of time transpiring in the universe before the sun and the earth in our galaxy, the Milky Way, start to form. Okay, then it turns out it's not that much longer for life itself to start forming. It's less than 1 billion years, actually, because a whole month is about 1 billion years. So in less than 1 billion years later, we have life forming on the earth, early life, okay? Well, then a lot of time goes by and life is evolving, and the earth is changing, and all kinds of things are going on. The dinosaurs come into being and all that stuff. But you would think, oh, that might happen here in October, November, but no. So much time has gone by. Another 3 billion years has to go by. And so it turns out that the development of life into a lot of various life forms as we know them today didn't happen until the 17th of December on this calendar, okay? And this is an event on Earth that's called the Cambrian Explosion. It happens at the beginning of the Cambrian era, and it's about 540 million years ago. And this is when all the various types of life forms that we know today came into being. I mean, many of them are extinct now, but the general body designs, if you will, you know, legs, fingers, fins, snakes, insects, all these different types of body types got sort of invented in a short period of time on the Earth in what's called an explosion of diversity of life called the Cambrian Explosion. And later, in a later lecture, we'll talk about it in more detail. Let some time go by and life comes out of the sea. First you get plants and animals, plants coming out of the sea. Then you get different animals coming out of the sea. And then we have basically the rise of dinosaurs around December 26. Now, we think of the dinosaurs as being way in the past. You know, they existed from about 200 million years ago to about 65 million years ago. And that turns out to be around December 26. So after Christmas on our cosmological calendar, dinosaurs don't come into existence until just after Christmas, okay? Dinosaurs become extinct on the 30th of December. That's about 65 million years ago. And I can't see what it says there. I think it says around 7 a.m. that they become extinct, okay? Now, if we want to talk about human history, it all happened on the 31st of December. And let's go to our calendar and look at the 31st of December in detail, okay? I think maybe it's easier to go backwards. Let's look at now. Now we have technology, we have society. You and I are here. We got Zoom. We're, you know, this high-tech species. We put humans on the moon. Okay. 1 second ago was when Galileo and Kepler were doing all their things. That, you know, corresponds to about 300-400 years ago, 500 years ago. 5,000 years ago was the pyramids. That would be 11 seconds in the past from now. And then the first agriculture arising, the first cities that had developed along rivers in the Middle East would have happened about 25 or 30 seconds ago. And then if you want to know when did the first humans evolve, well, that would be about 2 minutes ago. Okay, at 11:58 p.m. on December 31st, where now is basically midnight. So if you think about it, out of that whole year, it's only in the last 2 minutes, you know, if you're sitting there on December 31st at midnight, it was only at 11:58 p.m. that humans came into existence if the age of the universe was shrunk to a calendar year. And so that's modern humans, but humans themselves were around for a few hours on this scale, okay? And so basically 300,000, 400,000 years ago, we have early hominids arising on the planet. So somewhere around 9 p.m. is the first hominids, okay? Somewhere around 11:58 p.m., the first modern humans. And then all that time, a minute and a half has to go by on that scale. And then all of a sudden, bada bing, 25 seconds ago, agriculture, 10 seconds ago, pyramids, 1 second ago, the Renaissance, and then now, okay? And so that's how fast human evolution has been and how little time it has existed out of a year, okay? All right, so I have a video that I'm gonna link. I guess I don't have this one linked yet to Canvas, so I'm gonna get it linked. It's called the Lustrous Simulation, and it does a very nice little job. I can't remember if I have it linked already or not. You know, trying to do my best to keep up, but I'll have it linked for you by the time this module opens. And it shows the evolution of the universe with time. So you really should watch what it looks like and how this cosmic web formed from an amorphous gas of matter and dark matter. So at, it doesn't make a whole lot of sense to tell you all these details now because you're going to watch it later, but I just want to say that it does include the physics of gravity and the physics of dark matter, which we're not really talking about. It allows for star formation out of the gas. It does the physics of that. It does the aging process and dying of stars and the process of the stars blowing the gas back out. And that's one of the things you will see in this video that is spectacular, is you will see how gas gets ejected around galaxies themselves. And so the chemical elements that are built up in stars are distributed around there. And so that's going to be very important for you to watch this video after you watch the whole lecture, because I'm going to tell you about how the chemical elements that make up our bodies were formed in stars in the early previous generations of stars in this region of the galaxy, and how that gas got blown back out into the region between the stars and then got incorporated into the next generation of stars. Okay. All right. So that's going to be the history of the universe. And that gives you some idea about how long humans have been around in the universe. Okay, we're going to switch gears a little bit. So if you want to take a break, you could always take a break right here. This would be a good place to take a break. All right. And what we're going to talk about now is our Milky Way. We are going to talk about the cycle of stars. We're going to talk about where stars are born, how solar systems are formed, and basically, eventually, what other solar systems are like. Okay, then we're going to move on to part 3 of the lecture, which is going to talk about the cycle and how life fits in. All right, so let's talk about our own Milky Way galaxy. Again, it's a flattened spiral galaxy. So here's what it looks like as a spiral. This is an artist's rendition. We have no photographs of the galaxy from the outside of the galaxy. And you can see it has these spiral arms where there's lots of stars concentrated into these spiral arms. It is rotating. It rotates again on its around about 250 million years for one rotation. And so therefore the sun has gone around about 20 times in its life. Our solar system is out here, say, in a little spur of a spiral arm. It's about 30,000 light years from the center, give or take 28,000 light years from the center, okay? And if you remember, the whole galaxy is about 100,000 light years across. If you were to see it from its side, from the outside, it might look something like this. And you have a center region here that's kind of bulgy. And then here's our distance out to the sun and our solar system orbiting our sun, about 28,000 light years out. Here is the thin disk of dust, of which the dust and gas, cold dust and gas, that's the area where new stars are forming. We'll talk about that. The disk itself is only about 1,000 light years in height, and again is about 100,000 light years across. Okay. Now, you have no doubt seen the Milky Way in the night sky, I hope. This is a picture of a European space telescope, a European telescope called the Very Large Telescope Array for VLT. And this is in Cerro Paranal and in Chile, in the high desert, and very high on a mountain. And you can see that from there, you can see the Milky Way itself, and you see how there's that thin dust and gas in the disk. You can see that here blocking some of the stars that are along the spiral flat shape of the Milky Way. So it's very interesting that from within inside the Milky Way, you can see it as a band across the sky. that looks something like this. All right, this is a very, very interesting story. It's a little bit detailed, but this is, if you wanted to ever understand where you are in the galaxy and the universe, this is the slide that's going to do it. This is going to tell you where you are in the galaxy, and it's going to tell you where it is that stars form in the galaxy. Okay. This is a galaxy known as Messier 83, sometimes called the Pinwheel Galaxy. And you can see it's a spiral galaxy like our Milky Way, and it has two very dominant spiral arms. Okay, again, rotating around, say, every 200 to 300 million years. Okay, and what you see here are the cool dust and gas. That's these dark lanes. You basically are seeing them in silhouette against the background light that's in the galaxy itself. And you'll notice that you see these red splotches. Okay, these are called nebulae. And why are they red and why are they bright? And I'll tell you why. They are lit up gas clouds, and they're lit up because the gas is being heated and excited by the local stars that are near those gas clouds. Okay, so you have stars that are actually embedded within this gas, shining their light into the gas, and it makes the light, it makes the gas fluoresce in a sense. Okay, that you get electrons in the atoms being absorbing the light, and then they fall back down to their lower orbits and emit light out. And it turns out that most of that gas, 99% plus, is hydrogen. Okay, is the element of hydrogen, and the hydrogen tends to have its electron move up and down such that when it re-emits the light from being excited by the starlight, and it gets excited, and the electron goes up, then this electron comes down and emits light back out. It emits this red light. It emits this red photon of light. Okay, so that's why all these gas clouds appear red to you, because they're mostly made out of hydrogen, hydrogen getting excited and de-excited, and they're being lit up and powered by the local stars that are embedded in those gas clouds. Okay. And you can see that those red nebulae, if you will, actually tend to clump along the spiral arms, okay? You know, you might see the occasional one sticking out on a spur of some sort, but for the most part, you see them clumping along on the spiral arms. So the spiral arms have cold-ish gas and dust in them. They have regions where new stars have formed and they light up the area around them and they glow red. These are called nebulae, okay? And then you have a lot of stars themselves, and they all seem to congregate along these spiral arms, okay? There's a lot of dynamics as to why those spiral arms form. I'm not going to get into that. But let's take a small chunk of one of these spiral arms that tends to be fairly active, okay? So we'll take this little region here and we'll blow into it and look at it in detail in this photograph up here at the top in the center. And again, we see these little red clouds that are lit up by the stars that are embedded in them. And let's look at this one in particular, where we can see that there are some stars embedded inside this very bright red emitting nebula. So let's examine that in more close up. And so now we can see that here's the stars that are lighting up the gas. You can see that these areas where they are getting illuminated are quite bright, and the rest of this gas is glowing red from the being excited by the starlight. And so whenever you see these pretty pictures of red clouds, normally that's what you're looking at. You're looking at these lit up gas clouds that are basically stellar nurseries. They're the leftover nursery of where stars formed. And so what has happened here is that the stars have formed in the gas, and when they lit up, the light starts to push the gas away. and clear the space around where the stars were born. And so here you can see this is happening, that the gas is clearing out from where the stars were born. And you can see, for example, these very bright areas where the gas is being pushed away from the stellar cluster or cluster of stars, okay? But let's go and look at one of these little areas that's not fully developed yet, say that's still a bit of a stellar nursery. And we might say, well, okay, this is what happens when stars are formed and they take their womb or their cocoon and push it away from them, and then they're exposed, and then the gas around them is this bright red. What about where the stars form themselves? They form in the colder, dustier, cold gas, okay? Basically, these dark clouds that you see strung together along the spiral arms. So if we take a look-see at a little area off to the side here from our brand new stellar cluster, we have to go and probe down into the dark clouds that are cooler. And what we see is in this picture are these little bright spots of little stars that have just formed. Gas has collapsed under gravity, and then the gravity has made a compact ball of gas, and something very amazing happens. A process called nuclear fusion happens. It's a nuclear process that emits energy in the core of the star, and then it causes the light to actually work its way out to the surface of the star and then make its way out into space. And that's what makes the stars shine and be stable against gravity. So here's an example of a star that is just emerging from its stellar womb, okay? And if we took an example, close-up picture of it, it might look something like this here, in this picture in the bottom center, and you can see little stars that are just forming and emerging from these gas clouds, okay? And then eventually a whole bunch of them will be born, and then they'll blow the gas away and you have stars be formed. So this is happening, this process that we zoomed into is happening at all locations along these spiral arms, okay? And so you can see that galaxies are truly a factory for turning gas into stars, okay? And when stars form, it turns out that the gas around them might form planetary system. So that's the next thing we're going to talk about, is the formation of the planetary systems. So you've learned now a great deal about where we are in the galaxy and how the galaxy is structured in the way that it forms stars, and why you see these red clouds and the spiral arms. Okay, so let's talk a little bit about the formation scenario. Okay, you kind of start with this ubiquitous amorphous cloud of gas that's cold, and then you get condensations in it, and then you might see some of these condensations look something like this, okay? And in these condensations, then they continue to cool under gravity, the gas collapse. Eventually, the core of it heats up to the point where fusion can happen, and then it emits light and forms a star. So here is a blow up of one of these advanced stages of star formation, and you can see that the star is not yet shining in here, but you formed a rotating disk that has the star at the center, and you have all of this gas and dust out here, and probably ice as well, excuse me, and it's rotating around the central condensation where the star is going to form. And so this is, if you will, a primordial solar system, okay? And we think that these are the objects that then turn into solar systems like our own. Now, this theory has been around a long time, and it's similar to this diagram here, where you start at the top and go down to the bottom. You start with your amorphous cloud at the top. Gravity starts to take hold and things are falling inward toward the center. And as they do that, they flatten out, start to spin. much like a ice skater starts to pick up spin as she brings in her arms. And so you get a flattened rotating disk. The star will form in the center where the greatest concentration of matter is. And then you get sort of ice forming in the outer layers, which might later become cometary or small bodies of comets and things like that. And you have toward the inner part warm gas and things like that, and rocky material that's heavier. And the idea was that you would then see small condensations form where planets would form, and you would get rocky planets out in the inner part of the solar system where you had the rocky material, and in the outer part of the material where this was icy and thin gas, you would get these very large Jovian-like planets like Jupiter and Saturn and Uranus and Neptune. And then you would have a solar system like this down at the bottom where you've got this outer ring of cometary material or leftover debris, asteroid field way out there. And then you would have some planets orbiting around it. And you'd have a solar system that would exist for, say, maybe some 5 or 10 billion years until the star decided to die. And we'll talk about that next. This is called the Nebular Hypothesis. It's the idea that the gas comes down, forms a disk, and then the star forms in the center, and the planets form shortly thereafter in the disk. Okay. Now, when we launched the Hubble Space Telescope in 1993, and it finally got clear vision, we were able to start to see a lot of these and peer into the gas clouds and see a lot of these proto solar systems forming. Okay, and so you can see here's a perfect example of a flattened one with a disk. Here's another one. Here's another one. You can see that the star seems to maybe have just ignited, lit up. Here's another one. Okay, so you can see some of these form really nice disks. Some of the other ones you see, it's very, very strange. They almost look like the gas is being blown away from them. Okay, so a star formed, but the gas is being blown away. And guess what, ladies and gentlemen? That can happen. And the reason it can happen is because, you know, you're in a stellar nursery and you're forming into a star and you've got a nice dust gas disk around you and you're like, hey, I'm going to make planets as soon as I get myself formed here. But some big star in your neighborhood of your gas cloud formed before you, and it lights up and it starts shining brightly and it starts pushing the gas away from it, and your little gas disk around you starts to get blown away from you before it can form planets. Okay, so that's kind of a bad thing if you want to form planetary systems, but it can happen. And so here we see that some stars, they don't suffer this process. They get lucky, they form disks around them and probably planets. And some of them, they have a lot of their gas blown away, and so that the disk doesn't seem to be able to form because a nearby star is basically blowing it away. And the question is, you know, what fraction of them do form planets and what fraction don't? And it turns out that we want to answer that question. So we've been thinking about it. Now that was state of the art in the 1990s, all the way through to about 2013. And it took 2 decades, but people built this telescope in Chile called ALMA. And it looks in the microwave part of the electromagnetic spectrum, not the visible. And same light energy that you use for your microwave oven. It's kind of near the radio waves. And you can see it's a big array of antennas that it can be used together as one big telescope, okay? And the process called interferometry. They can tie all the telescopes together and make them sort of like one big telescope, therefore you can get very sharp vision. We talk about this in a coming chapter. And lo and behold, we started to get images of these disks that were around these forming stars, and it blew our brains wide open. You can see that some planets have formed in here and cleared out little areas where the planets have formed, and then you see the dust rings between where the planets have formed. And that's a simplistic version of what you're seeing there, but you have to understand that indeed you are seeing rings that are shepherded into their thin rings by mass concentrations such as planets and things like that. Here is a face-on version showing the central star, and then out here probably a forming planet somewhere out here in this latter ring. And then you can see sometimes we catch them a little bit on their edge as well. These are pictures that have only been out in the last 5 to 7 years. And we really, for the first time now, can measure the structure of the shapes of forming solar systems. Again, right at the cutting edge of human knowledge. It's a spectacular step in our understanding of how planets form. So let's take a look at our solar system. I think that everybody's seen this sometime in 4th grade or 5th grade. And at one time you probably knew it cold with the back of your hand, but maybe not so much anymore. So our solar system is structured as follows. It has a large central star, followed by Mercury, Venus, Earth, and Mars. Those are what are called the terrestrial or rocky planets. And then Jupiter, the first gaseous planet, Saturn, Uranus, Neptune. And then there used to be a planet called Pluto. And then there are some other small bodies like Eris and Ceres that are sort of Pluto size. These are now termed dwarf planets. I'm not going to get into the whole Pluto debate, but eventually when we talk about solar systems later, around toward the last few weeks of the course, we'll talk about the demotion of Pluto and why that might make sense to you, or hopefully I can make it make sense to you, why Pluto was demoted to a dwarf planet. Okay, these distances are not to scale, but the sizes of these planets and the sun are to scale. So it can give you an idea of how big the Earth is compared to, say, the sun. And you can see there are these flares that come off the sun, sometimes called prominences, that are so big that they dwarf the Earth in its own right. Okay. Now the structure of the solar system is on a scale like this. So here we have the planets to size scale, but not to scale in terms of their relative distances from each other. Here we have them in scale of their relative distances, but not by their relative sizes. If on this scale, if you go from the sun to Pluto, the planets would be so small you couldn't see them. Okay. Here is one astronomical unit where the blue dot is. That's one astronomical unit. Out to Mars is 1.52. Then there's the asteroid belt. Then Jupiter at around 5.2, Saturn at around 10, Uranus at almost 20, Neptune at almost 30, and Pluto out to 40. I think I said some numbers earlier that might have been a little wrong out there. Okay. So the thing is, you can see is that the inner solar system is grouped very tightly here with one AU within 10% of the distance just to Jupiter, and 0.5% out to, or I should say, to Saturn, and 0.5% of that distance all the way out to Uranus. Okay, so let's look again at that scale a little bit more. This is a nice satellite image of the campus centered on the astronomy building, but of course, and on this scale, one astronomical unit, okay, you remember that number now, is about 7.5 meters, okay? So 7.5 meters, 23 feet or something like that, okay? Okay, so what we're saying is that if you stand on the corner near the astronomy building and you walk 20 feet, you've walked from the sun to the Earth's orbit, okay? Then you have to walk halfway down Fringer Mall just to get out here to Jupiter, and then further down to the engineering building just to get out to Saturn, and then all the way down here to Uranus, and then all the way past Stewart or Espina Street, sorry, to get to Neptune's orbit. Okay, now you can see that the outer solar system is quite far. So you're literally walking a quarter of a mile to get out to the outer solar system, whereas you only had to walk about 10 steps to get out to the Earth's orbit from where the sun was. So I'm trying to give you a feeling that, you know, if I walk across the room I'm in from one side to the other on this model, I've walked from the sun to the Earth, but then I have to walk another quarter mile to get out to the outside of the solar system. So it's very, very spread out, okay? Okay, now let's talk about the discovery of other planets in our galaxy, all right? There was some activity that happened in the early 90s that gave some suggestion that people were starting to see the formation of planets because they could start to see those dust rings or those dust, those little planar primary proto-solar systems I was telling you about. Then in 1993 and 95, we started to really see them with Hubble. And then ALMA came in around 2012 or 2015. But in the meantime, we also built a space telescope called the Kepler Space Telescope. And it was basically designed to find planets. And the way that they designed this experiment, you have to imagine, you know, how would you find planets? You have to think that up, right? They said, what we're going to do is we're going to get a telescope, we're going to point it at a small region of sky. And it turns out this region of sky is near Cygnus the Swan and off the side from the Milky Way in that constellation. We're just going to point it at that little field of stars and never look away and never blink. Okay, well, they blink a little bit because they would take images, you know, fast images, like one every few seconds, long images, once every hour or something like that, okay, or once every 30 minutes. And then they could mix up the different lengths of exposures to study the steadiness of the light, how the brightness might change in each of these stars in the field. And they just studied it and pounded it for 9 years, okay? Taking these pictures of these stars in this one field. It's called the Kepler field, I know, brilliant name. So if this is our sun, it's basically looking out in one direction and catching a star field. Now it can see, it doesn't just stop some depth, but it does see bright stars out further and dim stars in closer, okay? And if you look on the sky, here's the dust lane of the Milky Way, and this is the summer triangle of Cygnus the Swan and Altair, and then it's not showing Vega. Oh yes, there's Vega, the star Vega. This is the summer triangle, Vega, Deneb, and Altair. You can see them as a huge triangle in the sky in the summer, and it goes right across the Milky Way, projected on the sky. And then over here on this arm of Cygnus the Swan, which is basically a duck flying this way, here are the wings, here's the head, and here's the tail. And on this wing, out here is the Kepler field where all these stars have been studied, okay? And this is what the satellite looks like before it launched into space. It has discovered thousands of solar systems. How does it do it? It can only discover a special class, or I should say a special subset. It can only find solar systems for which the planets are orbiting edge on to our field of view. If the planets are orbiting this way, if you can see me in my little window, okay, then Kepler is not going to find them. But if they orbit this way, they're going to find them, because once in a while, every orbit, the planet will pass in front of the star, and when it does, it dims the star because it blocks some of its light. So this here is a diagram of a planet. We're looking at it edge on the plane of the planet's orbit, passing in front of the star. And here's the starlight. let's say the starlight has this amount of brightness, and then when the planet's not in front of it, it has this amount of brightness. When the planet passes in front of it, the brightness goes down and makes some minimum because of this planet blocking the light. And then as the planet comes out, it's moving around this orbit this way, okay, like this. And as the planet blocks the star a little bit, not all of it, but some of it, it occults it. You get some of the light brightness of the star is blocked out. And then as the planet continues and moves back out here, it's not blocking the light anymore. You can see that you're bright. So this is a time sequence. And basically you take a photograph of the star at this time, at this time, at this time, at this time. You measure the brightness. You get a little noise in your measurements because you can't make a perfect measurement. And then all of a sudden, as time goes by, you're marching by in time this way, the planet's crossing in front, the light is dimming, okay, and then it reaches some minimum, and then it starts to brighten again as the planet exits from blocking the light, and then as time goes on, you see the brightness of the stars holding pretty steady, okay? When we see this dip, we know that a planet passed in front of the star. We have discovered a planet, and we also now can tell you how long it took for the planet to cross in front of the star. And it gives us an information about how big the planet is. By how much the star light dimmed, we get information on how big the planet is compared to how big the star is. And then because the planet goes round and round and round and round and round, we'll see the dip. And then the next time the planet comes around, we'll see the dip again. And when the when the planet comes around again, we'll see the dip again. And so we watch the dip with time, dip again with time, dip again with time. And so we know the period at which the planet orbits, and then we can use Kepler's laws, and we can figure out how far away the planet is from the star. And we got all kinds of information about the masses. We get Newton in there, get Newton's law of gravity in there, and we figure out the masses of the planets. We get Kepler's law, figure out how far away the planet is, blah, 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 all kinds of stuff. And then we say, hey, we discovered a planet. Its mass is this much. It's that far from the star. Its orbit is elliptical by 5%. You know, all this stuff, we know it. We put it in a catalog and we move on to the next one. Okay. Now, why is this interesting? Because we're going to talk about whether the planet might be able to harbor life, might be habitable. And there's a simple thing that we talk about, which is the Goldilocks zone. It's called the habitable zone. You can imagine if you're a planet orbiting a star and you're in very close to the star, that you're going to get a lot of heat from light in close to the star. And so we would say that that's too close to the star, too much light energy, planet's going to be too hot, okay? And you're going to be like Mercury or you're going to be like Venus, all right? Mind you then that if you're very, very far away from the star, orbiting very far out, then the starlight has weakened to the point where maybe that planet is just too cold all the time. And so we would say that you're outside the habitable zone, and maybe you have a permafrost, and you might end up something like Mars is, where you're a cold, desolate planet. Now, not to give Mars too much hassle and Venus too much hassle, it's not their fault, but we're going to find out that in the past, they both were probably had oceans on them, and they might have been classifiable as habitable, because it turns out that the sun and stars brighten as they age, and so the distance that is the Goldilocks zone moves away with time slowly. But if you happen to be in the just right area, which the Earth is, we call this the habitable zone, and this is a region where you could have liquid water on the surface of your terrestrial-like planet. We call the habitable zone. So what we're looking for, ladies and gentlemen, is when we find planets around other stars, say with Kepler, we're asking ourselves a very simple question. Given the luminosity and brightness of that star, how much energy it's emitting, where's the habitable zone? And then did we find a planet in the habitable zone, in the Goldilocks zone? Okay, so let's take a look at that just a few cases. All right. All of these stars got named Kepler some number because there's thousands of them in the Kepler field. So this is Kepler number 47. Okay, the star itself is always called A, or they just leave it off, Kepler 47. And the planets then, in the order that they're discovered, are called B and C and D and stuff like that. So here's Kepler 47. 2 planets have been discovered around it, B and C. Okay. If you look at Kepler 47, it's got this inner orbit. And if you look at Kepler 47c, it's in this outer orbit. It turns out that Kepler 47 is a binary star. It's a major star with a small red star that orbits it. So this is a little bit different than our solar system, but there's a little red star that orbits around the main Kepler 47 star. But B here is in this orbit and C is in this orbit. This green area for Kepler 47 is the habitable zone I was talking about. And so what we see here is Kepler 47 is orbiting firmly within the habitable zone of Kepler 47. So 47c may be a planet that has liquid water on its surface, okay? And where there's liquid water, maybe there's life. And we have to go to the next step and say, can we design an experiment now to study the planet itself and determine whether there's biomarkers on the planet? Is there liquid water? That's a nice indicator. But are there other indications that there could be life? And we will talk about those later in the semester, are what are called biomarkers and how do you measure them? And the fact that within 10 years, we will have hundreds of planets measured and we will know if there are biomarkers on those planets. We'll know hundreds of planets in 10 years and obviously in 50 years, thousands more that have water on them, liquid water on their surface. So, you might want to catalog those for someday when you want to escape the planet and go find some Garden of Eden somewhere. This is the relative, the bottom of this slide shows the relative size of the habitable zone for the Earth solar system. Okay, so you can see Mercury's inside, Venus is just inside, and Earth is down here. And they show Mars in the habitable zone, but this is a bad drawing actually. The habitable zone is really, as we understand it, is a little bit closer to the inner region of Earth's orbit and in somewhere out here before you get to Mars's orbit. So it's really much thinner. But this shows you the concept of the habitable zone for the solar system versus that for 47, Kepler 47. Here is another version that we're showing. This is Kepler 186. Okay, this is a small dwarfy star, much smaller than the sun. And you can see that several planets have been found around Kepler 186. And of those, F here is firmly in the habitable zone. And so it looks like it might be a good Earth planet-like candidate. And so in the future, we will be studying Kepler 186F in great detail. Okay, here's one more. I believe this is the end of our tour so that I don't go through all 1,000 of these. This is the Kepler 11 system. This is a sun-like star. It has the same sort of mass and luminosity or energy output as the sun does, and it has multiple planets as well. But what I'd like to show you in this case is that they are all well within the inner region of the habitable zone. So here is Mercury's orbit, and here is Venus's orbit, and you can see that even this outer planet of the Kepler 11 system is just outside the orbit of Mercury. And most of the planets are orbiting closer to the star than Mercury does to our own sun. So not all these solar systems are favorable or have habitable planets. And we tend to find a lot of planets that are in close to their parent star. At the end of the semester, I'll be talking about this in detail. Oh, I lied. We have one more, the Kepler 62 system. This is 1,200 light years away from Earth, and again, has 2 planets, E and F, that reside in the habitable zone. Now, wouldn't that be cool? I mean, imagine if we were in a solar system with 2 planets in the habitable zone. We could just, I mean, what an incentive. Instead of going to the moon and picking up some rocks and then coming home and never going back again, at least that's the way it seems, we got this situation where, you know, we could hop over to another planet. Imagine if we could go to Mars, and Mars was already had oceans and water. And, you know, I hate to think of the way we would exploit it, but we'd have a whole nother planet. So, you know, the Elon Musk thing of going to Mars, people wouldn't be snubbing their nose at that. Okay, well, you got to terraform Mars. Well, okay, just an engineering project. But what if it was like our Earth, you know? I always want to call them Class M planets after Star Trek, because they call Earth-like planets Class M. And so I keep wanting to say Class M, but that's ridiculous. So anyway, 2 Earth-like planets around Kepler. So lots of variation out there in the galaxy with planetary systems. Again, something we've only known in the last decade that I'm teaching you now. And then also the fact that we only know several thousand of them in a galaxy with over 100 billion stars, one galaxy, which is one of 100 or so billion in the whole universe. Okay, this slide, again, this might be another good place for you to take a pause. We're heading into the home stretch for our class. And so this may be a region where you want to take another breather. And so, hey, that brings me to the magic word. I'm going to call it home stretch. So here we are at the home stretch. That's the magic word, home stretch. And we are going to go into our home stretch of this lecture. So I'm as excited as you are because I've been talking for a long time. Okay. Now what we want to do is look at the context. I've talked to you about the structure of the universe. I've talked to you about the age of the universe. And I've given you some idea of the countless number of stars there are in the universe. And I've talked to you about how planets and stars form. Eventually, but I haven't talked about how they die. And I haven't gone into that detail yet. We'll go into that detail later. But let's just say that I have mentioned that planets and stars have a lifetime, okay? Like our solar system will last about 10 billion years. It's 5 billion years old now. It will last about 10 billion years, and then our sun is going to basically eject its gas and vaporize the planets and put that gas back out into the galaxy, from which the chemical elements in your body will now be drifting in space in gas clouds, which probably will end up forming new stars, and you will end up either in a gas cloud in space, or in a star, or in a planet, or maybe in another life form. Some of your elements will be in another life form. So life goes on, and that's what your chemical elements will probably, that's their fate. So let's talk about that cycle and talk about this system of the universe which has developed life. And this is our modern view of why and how we got here, and the process that takes place. It comes back again to the video you saw of Jill Tarter, which if you didn't watch it, I suggest you go back and watch it. Jill Tarter's I Wish TED Talk, it's in Module 1. If not, watch it again. It's fantastic because with this new perspective that you've learned from this lecture, it will mean a great deal more what she's talking about. You have a much better context on which to understand her words. And one of her phrases was, if you give a hydrogen cloud a long enough time, it starts to ask who it is. And that's our story today. The universe is old enough that hydrogen clouds, those red bright clouds I showed you where stars form stars, and planets form, and then on those life forms, and they look back up and they say, what am I? And that's this slide, that's what the story is. So let me go through the story. Upper left, we have a representation of an expanding universe that once in the past was smaller, everything was more compact and closer together, and it has been expanding with time. And each of these dots represents one of the, say, 400 or 100 billion galaxies that exist out there. This is just a cube being expanded. The universe is not a cube, but it's just a, artist rendition of, if you took a cube of the universe out of the universe, this, and it let it expand, that's what it would look like. And in that cube, or that little region of space that's expanding, you then see these hundreds of billions of galaxies. Here's a galaxy like our Milky Way. That's one of them that's sitting in there. Spiral galaxy, forming stars in the way that we talked about, forming planets in the way that we talked about, okay? There's 100 billion of these in the universe. There's about 100 billion stars in each galaxy. That's just a coincidence by round numbers, okay? And if you look at the formation of just one of these 100 billions of stars, it might look something like this, okay? And this is the cycle that brings up life, okay? Hydrogen cloud condenses down to form a star. You get a disk around it that's going to form planets. You get the star in there. Sometimes the star gets these little jets as it's forming. It's due to magnetic fields that are spinning and things like that. But that planetary system will form, and then here you have this image here showing the Earth with its moon orbiting around the Earth, and the Earth orbiting around the sun, and then it's in a planetary system, and this goes on for about 10 billion years. And that's enough time for life to form, maybe intelligent life, okay? And on that life-bearing planet, perhaps intelligence forms, and we can move over to here. And at this stage in this cycle that we're going to talk about the rest of the cycle in a minute, at this stage of the cycle where you've got planets orbiting around the star that formed in this region of the galaxy after billions of years, okay, another several billion years go by and some life form might learn how to build a telescope and be like Galileo was 400 years ago and look out at the universe. Now, this is the interesting thing, is that there's no, in this picture, there's no external intelligence that has created consciousness. That somehow the laws of physics are such that you get abiogenesis, you get reproductive biochemistry, i.e. life. And from that, the awareness happens, because life would, to survive, is better if it's responsive to its environment. That means nerve impulses, that means responses to stimuli from the environment that probably then will come to some central location, which would be like our lower brain. And then eventually maybe more brain will be built as a mechanism that helps a creature survive. And then eventually that brain might become intelligent enough and developed enough to actually look up into the sky and look back at the universe and find out that its brain has a morphology of dendrites and neurons that mimics the overall structure, a large-scale structure of the universe itself. But in the process, that's you and I. We are the hydrogen cloud that one day looked up and said, who are we? What are we? What are we doing here? How did we get here? We can even ask why. Unfortunately, we have not developed a system yet to answer the question why, except for religion. Religion, however, is something that is not exactly a reproducible system. It has its service, but it doesn't necessarily let us ask any more questions other than the why question, and provides an answer that we cannot necessarily verify the answer to. Okay, so that's a spectacular situation where the universe itself, that's us, our minds, is the universe itself. We're not outside the universe. We're not some intelligent thing that got put in here by the an intelligent maker. We are the universe itself. My mind, your mind, are pieces of the universe that form a consciousness that look back out, and we are the universe itself saying, what am I? What is this? How did this come to be? Okay, how did I come to be? Okay, now let's go back and finish the process on the lower left diagram here, which is we've made it all the way through to this point where we're sitting on a planet now asking, and we are the universe asking, what am I? But eventually this star is going to die. One of the ways that stars die, and it's shown in the next panel, is they go boom, they blow up, okay? I'm going to show you in the second to last slide today, which is only a couple away, that stars die in two different ways. They either die gently or they die catastrophically. Our sun will die gently. Again, I'm not going to test that now. I'm just telling you that now, and we're going to talk about that in detail later in the class. But stars will die, and when they die, they move their gas back out into the solar system, and then out into space. Okay, and so here's an example of a star that went boom, and it's blowing its gas back out into space. And then eventually that gas will form new stars. The new stars will form planets. Maybe life forms will ask, what am I? And then they'll die and they'll cycle through again. And that is happening in these galaxies over and over and over again on the timescale of billions of years as this galaxy turns gas into stars and planets. Planets go through their cycle, and then stars go through their cycle. Then they die, turn back into gas, and then form and get incorporated into the next generations of stars. Okay, and all this is happening on little local areas. Again, over and over and over, stars are born and die and form solar systems. Okay, so that's our picture, and that's our context for life in the universe. And now really we've come to the real walk-away information on this slide about how we are connected to the universe and how life in the universe is connected to it. Now, there's one last piece to the story that I now want to talk about, okay? And that is this cycle of stars and the fact that the chemical elements in the universe are forged inside of stars due to this process I talked about earlier called nuclear fusion. And I'm not going to get into the details of nuclear fusion, but I want to talk about the life cycles of stars briefly that fit into this previous slide in this cycle here. Okay, you form from a gas cloud. That's what's over here on the left. Now, it turns out that you can either form into a small star that's low mass, or you can form into a big star that's high mass. Okay, now that's not to say you're either small or you're big. There's a whole continuum, but there's a dividing point where if you're below a certain mass, you're considered low mass, and if you're above a certain mass, you're considered high mass. And that turns out to be about 8 times the mass of the sun. That's the sort of split. So if you're more than about 8 times the mass of our sun, then you are a high mass star. And you go through this sequence. When you're born, you start nuclear fusion in the core, and the nuclear fusion is basically the smashing together of hydrogen atoms from which you formed, making helium. The helium smashes together and makes carbon and oxygen and nitrogen, and you can eventually go to the point where you're making silicon and neon and aluminum, okay? And all the way up to iron. And these massive stars can forge iron and all these other elements like magnesium and silicon and carbon and nitrogen in their cores, and they make those elements of the periodic table through this process of sticking hydrogens and heliums together. And eventually it runs out of the ability to do this. And its core collapses and it explodes in a huge supernova explosion. So that's what this stage is here. So in the early universe, stars formed out of hydrogen and helium. That hydrogen and helium was built in the Big Bang, and then that was 13.6 billion years ago. And then that hydrogen and helium formed into gas clouds and formed stars. The stars did nuclear fusion in their cores to take that hydrogen and helium and form some of it into carbon, nitrogen, oxygen, silicon, magnesium, and iron, and all that stuff. And I probably repeated 5 elements. Then it runs out of the ability to do that for reasons I won't explain, and it explodes. So now you've taken all of those new chemical elements that you built up on the periodic table, you know, and you've blown them back out into space. And now they're going to form new stars that have gold and silicon and nitrogen and carbon in them, and gas disks that have carbon and nitrogen and oxygen in them, and planets that form from silicon and oxygen and carbon and nitrogen and all these other things, phosphorus and gold and whatnot, platinum. And then maybe life forms from those chemical elements, the carbon, the nitrogen, and oxygen, like we do. We breathe nitrogen and oxygen. We are made mostly of carbon and hydrogen and a lot of oxygen, okay? Those chemical elements, the carbon, the nitrogen, oxygen, were all forged in the previous generations of stars in their cores from nuclear fusion, which then got blasted back out into our region of the galaxy, which then our star and our planet and us formed. So we literally are made out of the chemical elements that at one point in time were in the cores of stars in the past in our region of our galaxy. Okay. Now, the hydrogen in our bodies all came from the Big Bang. Those atoms are 13.6 billion years old. The carbon, the nitrogen, the oxygen, and all those elements, the iron, magnesium, they came from a previous generation of stars. And that was probably blown into this local region of the galaxy about 6 billion years ago. So those elements in our bodies and the ones we're breathing and the silicon that's running your computer chips right now, those are all around 6 billion years old, okay? Now, I don't want to talk about too much what's going on here, but after the supernova goes off, the leftover middle of the core of the star can either form a black hole or something called a neutron star, okay? And then, of course, all this gas returns to this nebula of gas in our local region of the galaxy and then forms new stars. Low mass stars have a different direction. They also do nuclear fusion. They also create carbon and nitrogen and oxygen, but that's about as far as they can go, and then they run out of steam. So they don't build magnesium and iron, they just build up to carbon and nitrogen. And when they do so, then eventually they kind of hiccup and blow their gas out very gently, and this is called a nebula, a planetary nebula, and it evaporates the planets around the star, and the gas kind of gently goes back out into this region of the galaxy. This is the fate of stars like our sun. Okay, we're not going to go boom like a supernova. We're going to go poof, 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 and make a nice evaporating nebula, and our solar system will gently be pushed in the gas form back out into the between the stars. Okay, maybe so the leftover core of that process of our sun will become something called a white dwarf. This is a very hot remnant of the star that's around the size of the Earth. And we don't need to concern ourselves too much with that. We'll talk about that later in the class as well for our sun, but this gas, again, gets reincorporated into nebulae from which stars form in the spiral arm of our galaxy. So, recap. Stars form. The early generation of stars just formed from the hydrogen and helium of the Big Bang. They do nuclear fusion, create elements along the periodic table that before that didn't exist, carbon, nitrogen, oxygen, and things like that we are made of. And then The stars die either as a planetary nebula or as a supernova explosion. Take the elements they formed in their cores, push them back out into space. We now have gas clouds with carbon and nitrogen seeded with elements from the periodic table, from which now a second generation or third generation solar system like ours forms, and life like us forms with those chemical elements that were formed in the stars. So we are star dust in that sense. So when you say, are we stardust? This is the story as to how we're stardust, okay? That the periodic table of elements that we are formed from were created in the nuclear fusion cores of previous generations of stars. This is a diagram showing you a little bit about that process. It's just this idea that elements crash into each other in the hot gases in the core or in shells around the cores of the star, and you can form nitrogen into fluorine and fluorine into oxygen and oxygen into neon by adding helium nuclei to them, because they crash together and stick together. And so you get this area where in the interior of the star you have iron and nickel, silicon and sulfur, oxygen, neon, magnesium, and stuff like that. Now this is just the core of the star. The real star itself, if we were to draw in this diagram, would reach all the way out down, a mile down the street from you. Okay, the core is just this teeny little part in the center of the star, but you can see all this activity going on there. And then when the star blows up, kabooey, all those chemical elements go back out into space according to our story. So I believe this is my last slide. It's the periodic table. And one of the things that we have learned over just the last few decades is where these elements all came from. So they're color-coded by where they came from. And there's the walk-away information that I want you to understand is that they either come from the Big Bang. And what's that? That is hydrogen and helium come from the Big Bang. Very little of it comes from other places, okay? Then you have dying low mass stars, like our sun's going to be. Those are green. And so we see that most of the carbon in the universe comes from low mass stars like our sun's going to do, and nitrogen, okay? And then even some of these other elements like lithium and yttrium and niobium and other elements that we don't ever talk about, including barium, which of course is part of the Breaking Bad symbol, okay? And then exploding massive stars like the one we talked about that become the supernovae that make these big shells of all the gas chemical elements. They really add a lot to the periodic table, including some of the carbon, some of the nitrogen. They make mostly all of the oxygen. So you breathe oxygen and you breathe nitrogen. Most of the nitrogen atoms that you breathe came out of the cores of low mass stars that existed in this region of the galaxy. The oxygen all came from exploding supernovae. So there you have it. Now you know that your oxygen's from supernovae and your carbon and nitrogen are from low mass stars like the sun is going to do. The other thing is that water. You are mostly water, 70% water, okay? Water is made out of 2 hydrogen atoms and 1 oxygen. The 2 hydrogen atoms came from the Big Bang. They're 13.6 billion years old. And the oxygen came out of some supernova that exploded around 6 billion years ago in this region of the galaxy. And they somehow found each other and formed water molecules and then somehow got put into your little water bag called your body. So it's very interesting now. You understand much more about the chemical composition and your connectivity to various processes in the universe that happened before our star and our planet even formed. Okay, it turns out that we are mostly carbon, nitrogen, and oxygen. We also have a lot of hydrogen in us, and then a little bit of phosphorus. So we are stardust. We are cosmic dust from the Big Bang, the hydrogen in us. We are stardust in the sense that we are chemical elements, carbon, nitrogen, oxygen, and phosphorus. We're all forged in previous generations of stars. Our carbon and nitrogen mostly from low mass stars, and our oxygen and phosphorus mostly from high mass stars. And so there you have it. And you might be wondering, what's the phosphorus for? Well, you've heard of the ATP cycle. That's adenine triphosphate. And a phosphate is phosphorus with 3 oxygens bonded to it. And so those are very important for your metabolism. So phosphorus is very important. Also, we're going to learn our DNA, the backbone structure, if you will, the outer coil of it is made out of phosphate groups, which is phosphorus and oxygen. So phosphorus is very important for life. C, N, O, and P, and then hydrogen as well. And so that, ladies and gentlemen, does it today for our lecture. And hopefully now you have a much better appreciation for why we are star stuff, where the chemical elements of the periodic table came from, how they're related to the cosmology, how our own consciousness is related to these cycles, and where stars form in galaxies, how they form, and then how galaxies are related to one another spatially in a cosmic web, where we are relative to our local cluster of galaxies, 65 million light years in the suburbs from that metropolitan area of groups of thousands of galaxies in a cluster, and how it is one of many in the universe, and then how the universe is about 13.6 billion years old. So I hope you didn't miss the magic word. You'll have to, unfortunately, watch the lecture again, and I know that can be painful. And when we move on to the next module, we will be talking, I believe, about the Earth and its history, and talking about how we understand where we came along in that. So anyhow, thank you for listening, and I'll see you at office hours, maybe. And I want to say good luck with this module, and I hope you really enjoyed learning some of this astronomy. Thank you.